In this video, we're beginning our study of the limits of functions, and this is something we need as we move towards an understanding of calculus. So let's begin. Let's look at some function of x. In this case, I've drawn a parabola, and let's look at three different ways of looking at the rate of change of that function. Now, in previous units, you may have learned about the average rate of change, AROC. If we have a point x1, y1, and a point x2, y2 on this function, we were looking for the average rate of change between those 2 points. We would simply draw the line between those 2 points, which we call the secant, S-E-C-A-N-T, and we would take the slope of that secant, which is just the change in y divided by the change in x. And that value would give us the average rate of change between x1 and x2. And as you can see, that's not a very good estimate of what is really happening as we move from x1 to x2. But as we move x2 closer and closer to x1, for example, if we have a point x3 here, then this secant line will start to look more and more like the actual slope of the function at the point x1. And that was our next stage of development. We introduced the concept of instantaneous rate of change. And here we said, well, let's consider x1, y1, and let's choose x2 to be very close to x1. And now when we draw the secant, we're getting pretty close to the tangent to the function. So here we let x move a small amount, h, and this x plus h will be our x2 value. And then the slope of that line, it's still y2 minus y1 divided by x2 minus x1. But instead of y2, we say it's the value of the function at x plus a little bit minus the value of the function at x. And because we have to divide by the change in x, which in this case is simply x plus h minus x, so the distance we move in the x-axis is simply h. And for h, we've tended to use a value of 301, typically to give us a reasonable estimate of the instantaneous rate of change. Now, we want to move to the next and the ultimate level of accuracy, which is to find the true tangent to this curve, which is the real slope of the line. So we're trying to just touch the curve at one point and one point only, and that is the tangent. And the slope of this line we call m tan, the slope of the tangent, and that's the true rate of change of the function at x1, y1. Now to get that, we're going to use the instantaneous rate of change formula, except that we're going to let h get closer and closer to 0. And the way we write that is that this slope, this tangent, is going to be equal to, and we write it's the limit as h tends to 0 of f of x plus h minus f of x divided by h. So it's exactly the same as the IROC formula, except that we have this new piece at the front, this limit as h tends to 0 expression. And that's really why limits of functions are so important as we move into calculus. To get the true value of the slope of a function, we need to find the limit of this expression as h gets smaller and smaller, in fact gets almost to 0. Okay, so let's proceed. So you might be asking, what do you mean by getting closer and closer to 0 but never actually getting there? So suppose, for example, we had the simple equation y is equal to x squared, and we want to find the slope of that function at any value of x we choose. So here is y equals x squared, and we're looking to find the slope of the tangent at some value x. So if we use the expression that we just had, we would say that the slope of the tangent is equal to the limit as h gets closer and closer to 0 of f of x plus h minus f of x divided by h. And you might think, well, if I put h equals 0 into that expression, I would simply get f of x minus f of x divided by 0, and I would get 0 divided by 0. And clearly that is an indeterminate expression. We can't have a slope of 0 divided by 0. That's undefined. But clearly the slope of this function is defined at every point. So simply substituting in a value of h equals 0 is not giving us the information we need. What we actually have to do is expand that expression. So f of x plus h means put x plus h into the equation wherever there is an x. So f of x plus h means x plus h squared in this case, because the function is simply squaring what's in the bracket. Minus f of x, well, that's simply x squared divided by h. And that is the limit as h tends to 0. If we expand the bracket, x squared plus 2xh plus h squared minus x squared divided by h. Now we can see that we've got x squareds on the top, which cancel each other out. And what we're left with is the limit as h tends to 0 of 2xh plus h squared divided by h. And here's where it gets a little strange. We've got a common factor on the top and the bottom of h. And so we can divide all the terms on the top by h and the term on the bottom by h. And so we get the limit as h tends to 0 of 2x plus h. And if I let h become 0 now, I get just 2x. So this has given me an expression for the slope of this function up above at any value of x I choose. So if I choose to find the slope at x equals 1, the slope is going to be 2x, which is just 2. At x equals 6, the slope will be 2x, which is 12. Now, where people struggle a little in this last row of the algebra is that normally we are told that you cannot divide the top and the bottom of an expression by a number if that number could be 0. And in this expression here, we said we're going to cancel h's on top and bottom. So that means that h is not allowed to be 0 when we do that. So we're dealing with the limit as h gets closer and closer to 0, but not actually 0. And that allows us to cancel h on top and bottom. But then in the next step, we have this expression of 2x plus h, and we plug in h equals 0 to get 2x. So it's a little inconsistent, and this is, I think, why people have problems with limits, or one of the reasons they have problems with limits is that inconsistency. Again, we're talking about where does this function, this 2x plus h, where does it end up as h gets closer and closer to 0? And it's going to get closer and closer to 2x. Let's look at this example to understand visually what we mean by a limit. Here we have an interesting function graphed. It is a function because it passes the vertical line test so that there is only one value of the function for each value of x. Now what happens if we look at, let's say, the limit as x tends to minus 6 coming from the negative direction. So this little negative sign means we want to see where this function approaches as we come in from the left direction. So if we look at the graph, we're coming in towards negative 6 from the negative direction. And we can see that the function is smoothly approaching a value of negative 2. And so the function is well behaved on that left-hand side, and we can say that the limit as x tends to minus 6 from the negative direction is negative 2. But what happens if we approach that same negative 6 from the positive direction? As we approach from the positive side of negative 6, we're getting closer and closer to a value of plus 2. Even though the function does not exist at negative 6, because we show that there is actually a hole in the function at that location indicated by this open circle. So the function does not exist at negative 6 when we're coming from that direction, but the function is getting closer and closer to a value of 2, and therefore that is the limit of the function in that direction. Now, if we have a situation like this, where a function is tending towards two different values, depending on whether you approach a certain value of x from the right or from the left, that means that the limit as x tends to -6 for the entire function does not exist. For a limit to exist, we must be able to approach from either direction and arrive at the same value. Let's look at another location now. Let's look at the limit as x tends to -1 coming from the negative direction. So again, looking at the graph, we're tending towards -1. We're coming from the negative direction. So that means we're following the curve around and we're arriving at a value of +5. It looks to be well behaved, and the function does exist at -1, and therefore the limit is simply +5. Similarly, if we look at the limit as x tends to -1, but coming from the positive direction, we see that the function is well behaved at that spot, and as we approach from the positive direction, we end up at the same value of +5. And that means that the limit as x tends to -1 is equal to 5. Now let's look at a couple more locations to see what's going on. Let's try the limit as x tends to 2 of f of x from the negative direction. So we want to approach 2 from the negative direction. So here's 2, and we're coming from the negative direction. And we see that we're getting closer and closer, again, to a value of 5 at that location. On the other hand, if we look at the limit as x tends to 2 from the positive direction of f of x, we can see that the function approaches a value of 4. And again, since these two limits are not the same, we can say that the limit as x tends to 2 for f of x does not exist. Let's check a couple more locations. So let's look at the limit as x tends to 4 coming from the negative direction. So what's happening here? We're approaching 4 from the negative direction. So that means we're going in this direction, and we're getting closer and closer to a value of, let's say, 4.3. Even though there is a hole at x equals 4, in other words, the function does not exist at x equals 4, as we're approaching from the left-hand side, the value of the function is getting closer and closer to that value of 4.3. And that's sufficient to be able to define the limit. So we can say the limit is 4.3. Similarly, if we come from the other direction, the limit as x tends to 4 from the positive direction of f of x. Well, here we're coming down the curve in this direction, And once again, the value is getting closer and closer to that hole at 4.3. And so the limit is indeed still 4.3. And therefore, even though the function itself does not exist at x equals 4, the limit as x tends to 4 of f of x is 4.3. So a limit can exist even though the function does not exist at that point. And the last case to look at is the case where the limit as x is tending to 5 from the negative direction of f of x. And what we actually have here is an asymptote at x equals 5. So that means that as x approaches 5 from the negative direction, the function is heading off towards infinity. So there is no limit there. Similarly, if we were coming from the positive direction, we'd be heading off towards negative infinity. So that doesn't exist either. And therefore the limit as x approaches 5 does not exist. So that gives you a flavor of the different types of behavior of a function and the resulting limits of that function as we approach certain values. Let's now look at some strategies for finding the limits of functions. The first strategy is always to try plugging in the value. So let's say, for example, we have the function f of x is equal to 3x squared minus 5x plus 1. And we want to know the limit of this function as x tends to 2. The limit as x tends to 2 of f of x. So if we just plug in the value 2, we get 3 times 2 squared minus 5 times 2 plus 1, and that is simply equal to 12 minus 10 plus 1, 3. So polynomials, in this case a quadratic, are well-behaved functions, and nothing strange happens in terms of zeros divided by zeros, and it's a simple case of plugging in the value and you will get the limit as required. Let's look at another one. Let's say we want the limit as x tends to 0 of, let's say, the square root of x squared plus 5. So we plug in the value 0, we end up simply with the square root of 5. So again, that's a well-behaved function, and the limit is easily found by plugging in the value. Let's try one more. Let's try the limit as x tends to 3 of 1 divided by 2x minus 1. Now here we have a reciprocal function, and we know that such a function does have a discontinuity. This function will be badly behaved whenever the denominator is 0. So that means 2x minus 1 would be 0, or x is equal to 1/2. So if we were asked to evaluate the limit at 1/2, we would have a little more difficulty. But in this case, we're asked for the limit of this function as x approaches 3. And in that region of the function, it is well behaved. And so again, we can simply plug in the value and we get 1 divided by 5. So that's strategy 1, the simplest approach. Plug in the value, works for polynomials, square roots, reciprocal functions, anything where the function is well behaved. Let's now look at strategy number 2. What happens when you plug in the value and you get an indeterminate result? Let's say we have the limit as x tends to 3 of x squared plus x minus 12 over 2x squared minus 5x minus 3. So the first thing we do is try to plug in the numbers, and we end up with 9 plus 3 minus 12 divided by 18 minus 15 minus 3. So we get 0 divided by 0. 0. So we get an indeterminate value of the limit. So in this case, for polynomials like this, our next step is to try factoring. And the reason we do this is to hopefully eliminate the factor which is producing the zeros. So if we factor this expression in the usual method, we end up with x minus 3 on top multiplied by x plus 4, and on the bottom we get x minus 3 into 2x plus 1. Hopefully you all remember how to factor. If not, there'll be a video on that to remind you. So we're able to now write that the limit we're looking for is the same as the limit as x tends to 3 of this function. And now, this is where things get a little confusing for people. We're going to cancel the common factor on the top and the bottom. Those factors cancel, and we write that this is the limit as x tends to 3 of x plus 4 divided by 2x plus 1. Now you'll remember that when we usually cancel those factors in that fashion, we introduce a restriction on the function that says x cannot be equal to 3 in order to be able to divide top and bottom. But in the next step, now that we have factored the function and eliminated the factor that is causing the problems in simple substitution, now we do actually feed in the value 3. And that seems a little contradictory, and it's one of the things that confuses people when working out limits. In one step, we do something that forbids a value, and then in the very next step, we actually feed in that value. So I'm feeding the value 3 into this simplified expression. I'm ending up with 7 divided by 7, and I'm concluding that the limit as x tends to 3 of the original function is actually 1. So even though the function is not defined at 3, there is actually a hole at 3 if we drew this function on Desmos. All we're saying here is that as we get infinitesimally close to the value of 3, the value of the function is getting closer and closer to the value of 1, even though the function is not defined at that point. And as we saw in the earlier visual example, it's perfectly okay for a limit to exist at a certain value of x, even though the function does not exist at that value. And that's all that's happening here. Let's look at another example of that just to get you comfortable with this factoring technique. Let's say we have the limit as x tends to 2 of the function x cubed minus 8 divided by x minus 2. And again, we can see that if we first try to feed in the value 2, we will get 8 minus 8 on top, 2 minus 2 on the bottom, which is 0 over 0, and that is not a well-defined quantity. So we go to factoring. We notice that the top expression is actually the difference of cubes. It's important to be able to spot when you have a function like this and realize that it is actually x cubed minus 2 cubed. So you have a difference of cubes. And that allows us to factor the top. We pull out an x minus 2. And the second term, if you remember, let's write it over here, a cubed minus b cubed is a minus b into a squared plus ab plus b squared. So substituting in those values over here, that means we need an x squared, we need a plus 2x, and we need a plus b squared, which will be 2 squared or 4. And so again, we've identified a hole in the function, and we're able to cancel out those factors, top and bottom, and that means that x is not actually equal to 2. But that's okay because we're looking at the limit as x approaches 2, not when x equals 2. Limit as x tends to 2 of x squared plus 2x plus 4. And now we substitute in the value of 2, and we get 4 plus 4 plus 4 equals 12. So again, even though the function does not exist at x equals 2, the limit as x approaches 2 does exist and has a value of 12. Now let's look at a third type of problem. These are ones which include radicals. And remember that radicals are things that have this function square root, cube root, nth root in them. And typically we'll be dealing with square roots in these kinds of problems. And I want to introduce the term conjugate in order to do this. If you have a term in an expression, a plus b, then its conjugate is, you just change the sign in between the two components of the bracket. And similarly, if you have a minus sign, you would have a conjugate which is the plus sign. And why is that important? Well, we know that the difference of squares, a squared minus b squared, factors nicely into a minus b multiplied by a plus b. And this is a pair of conjugate terms as described above. And the nice thing is that when we multiply these two brackets together, the middle terms composed of a and b disappear, and we're simply left with the a squared term and the b squared term. And consequently, if we have a bracket that includes a square root, for example, and we want to eliminate that square root, we can multiply by the conjugate of that particular bracket, and then we end up with the first term squared, or root 3 squared would just be 3, minus the second term squared, and that would just be 1 squared is 1. And so we're able to turn these radical expressions with square roots into simpler numbers. So let's look at an example of how that applies to solving limits of functions. So let's suppose we're asked for the limit as x tends to 9 of the function root x minus 3 divided by x minus 9. So the first thing to do as usual is plug in the numbers and see what happens. Well, the square root of 9 is 3 minus 3 divided by 9 minus 9, 0 over 0. That's no good. That doesn't give us the limit. So can we factor it? No, we can't. Can we use conjugates to simplify the expression? Yes, we can. So let's do that. Let's multiply this top root x minus 3 by its conjugate root x plus 3. And whatever we do to the top of a fraction, we must do to the bottom in order to preserve its value. And now when we multiply together the top, we get the limit as x tends to 9 of root x times root x is just x. The middle terms disappear, and 3 times 3 is 9. So the top reduces to x minus 9. That happens to match one of the factors on the bottom. And so once again, we are able to cancel top and bottom. There's a hole in the function at x equals 9. So we know that in this function x is not equal to 9. But that's okay because we're looking for the limit as x approaches 9. So the limit as x approaches 9, now we can feed in the value of 9 to the remaining function, because we've taken away the part of the function that causes the problem. So it's perfectly okay to evaluate this function at 9. And this function, if we feed in the value 9, is going to be 1 over root 9 plus 3, which is 1 over 3 plus 3, 1 over 6. And if you're in any doubt about this stuff, go to Desmos, feed in the original function, and take a look at what's happening as x gets closer and closer to 9. There'll be a hole sitting at the x value of 9, but the function on either side of it will be approaching a value of 1 over 6 in this case. Let's do a second example of radicals, 3b. To make sure you're comfortable with this technique, we'll look at the limit as x tends to 0 of root 5 plus x minus root 5 minus x, all divided by x. And now again, we start by feeding in the value to see if we can get the limit simply by substituting in the value. Feed in a 0, we get root 5 minus root 5 divided by 0, we get 0 over 0. So that's no good. So now we know we can't factor, but we do have radicals, so we're going to use the conjugate approach. So the limit as x tends to 0. Now what is the conjugate in this example? You're not looking at the term under the radical, you're looking at the expression that has the negative between two terms. So this would be a and this would be b. So we need a plus b as the conjugate. So that would be 5 plus x minus root 5 minus x multiplied by its conjugate, root 5 plus x. We don't change any signs there. Where we change the sign is between the terms. 5 minus x. And on the bottom we need to do the same thing to preserve the value of the fraction. So that looks complicated, but it'll clean up. Limit as x tends to 0. Now these two terms multiply together to give 5 plus x. The middle terms all disappear, and the only thing you're left with is the last term, which would be the product of these two. So that would be minus 5 minus x. This is a squared minus b squared. And all of that divided by x into root 5 plus x plus root 5 minus x. Okay, now if we simplify the top, we've got 5 minus 5, and we've got x minus negative x. X minus negative x is the same as x plus x, so we end up with 2x on the top. On the bottom, we have x root 5 plus x plus root 5 minus x. So this is good. It's the usual situation where we have now extracted a common factor on top and bottom of the expression, and that is the problematic factor because it's when x equals 0 that we get 0 divided by 0. So here we are able to eliminate those as long as x is not equal to 0, and we're left with the simplified expression, the limit as x tends to 0 of 2 divided by root 5 plus x plus root 5 minus x. And now, because we've removed the problematic part of the function, we are able to substitute in x equals 0, even though the function doesn't exist at x equals 0. And we're left with, on the bottom, root 5 plus root 5. So that's 2 over 2 lots of root 5. 2's cancel, and that gives us 1 over the square root of 5. Now, when I was at school, 1 over root 5 was a perfectly good answer, but these days teachers don't like you to have radicals in the denominator. So 1 divided by root 5, we multiply top and bottom by root 5. So we end up with root 5 on the top. And on the bottom, root 5 times root 5 is just 5. So that's the limit of that function as x tends to 0. Once again, the function does not exist at x equals 0, but the limit does. Okay, this fourth strategy is a substitution. So if you've tried putting the value in for the limit and that hasn't worked, you've tried factoring, it's not a radical type problem, then this would be your next approach. So let's look at an example. We want the limit as x tends to 2 of x plus 25 to the power of 1/3 minus 3, all divided by x minus 2. And I think you can see straight away that we've got the cube root of 27 on top, minus 3, divided by 2 minus 2, and that's the usual problem, 0 divided by 0. So feeding in the value is not going to work. What can we do now? So we take this complicated expression here and we introduce a new variable. We say let u be equal to that thing, x plus 25 to the power of 1/3. And now what happens as x tends to 2, u will tend towards the cube root of 27, just putting a value of 2 in here. And so we can say that as x tends to 2, we're talking about u tending towards 3. So we can rewrite the expression as follows. It's the limit, not as x tends to 2, but as u tends towards 3 of, and on the top we have u minus 3. And now what do we have on the bottom? Well, we need to do a bit of substitution here. If we rearrange this expression for x, so we can cube both sides, so we get u cubed, and then take away the 25 is equal to x. And so on the bottom, where we have x minus 2, we can actually write u cubed minus 25 instead of x, and then minus 2. So that's the limit as u tends to 3 of u minus 3 over u cubed minus 27. And now that bottom expression should jump out at you as the difference of cubes. Usually in these problems we are looking to find a common factor, top and bottom. So we know that u cubed minus 27 is just a cubed minus b cubed, and that's a minus b multiplied by a squared plus ab plus b squared. So we can rewrite this as the limit as u tends to 3 of u minus 3 on top, and then on the bottom we've got the common factor we wanted, u minus 3, and then u squared plus 3u plus 9. And now we're back to the usual procedure. We've got a common factor top and bottom. Cancel those out as long as u is not equal to 3. And our limit problem reduces to the limit as u tends to 3 of 1 divided by u squared plus 3u plus 9. And now, because we've eliminated the problem factor, we can just feed in the value of 3, and we get 1 divided by 9 plus 9 plus 9, 1 divided by 27. And so the limit of the function as x tends towards 2 is 1 divided by 27. Again, if you want to verify that for yourself, feed the original equation into Desmos and take a look what happens. Okay, so there's 4 techniques. Unfortunately, we need more. Let's look at expanding the parentheses, expanding the brackets. So this type would be the limit as x tends to 0 of something like x plus 2 squared plus 4 minus 4 divided by x. Again, if we substitute in as our first attempt, we end up with 4 minus 4 divided by 0. That's 0 over 0. That's no good. And then we could look at factoring. There's nothing here to factor. And so what could we do? Well, we could do a substitution approach, but in this particular case, it's simply to expand the bracket. The limit as x tends to 0 of x squared plus 4x plus 4 minus 4 divided by x. The 4's cancel in this particular case, and we have a common factor of x, top and bottom. So that means we can divide everything on top by x. The x squared just becomes x. 4x just becomes 4. And we get rid of the x on the bottom. As long as x is not equal to 0, we can do that. And so now we are left with the limit as x tends to 0 of x plus 4, which if you put in x equals 0, it's simply equal to 4. So sometimes it's as simple as that. Our next example is a special case of trigonometric functions, and in particular we're looking at sine x over x, and we're looking at x over sine x. Now, without going through the proof at this stage, I'm going to tell you that the limit as x tends to 0 of sine x over x, if we fed in 0, we would get 0 over 0. But in fact, if you plotted this graph, you would find that As x gets closer and closer to 0, sine x over x gets closer and closer to 1. And similarly, the limit as x tends to 0 of x over sine x is equal to 1. So there are ways to prove that, but at this stage we're just going to give you those definitions to use to solve slightly more complicated problems. For example, if you were asked for the limit as x tends to 0 of sine 3x divided by x, all you have to do here is try to make this sine 3x over x look like one of the two expressions in the box. And we can do that by multiplying the bottom by 3. So we get the limit as x tends to 0 of sine 3x over 3x. Now we've introduced a 3 in the denominator, so we have to introduce a 3 in the numerator as well. And from our properties of limits, we know that the limit of a product is the product of the limits. So the limit as x tends to 0 of the number 3 is just 3. It's independent of x. So this is 3 times the limit as x tends to 0 of sine 3x over 3x. And this is 3 times 1 or 3. Because this expression here is the same as this expression here, except that we've substituted 3x for x. And as 3x tends to 0, x tends to 0, so there's no difference in the limit value. If you put in u equals 3x, then you would write the limit as u tends to 0 of sine u over u. And we know that this is equal to 1. So that's a simple way of solving that kind of problem. Along similar lines would be the limit as x tends to 0 of 4 sine 5x divided by sine of 4x, for example. Now we can rearrange this to take a similar form to the standard limits that we know. So it's x, limit as x tends to 0. We want 4x over sine 4x, and we want sine 5x over 5x. Now to get there, we've multiplied the top by x to give us 4x here, but we also multiplied the denominator by x over here, so those two cancel out, so that's perfectly okay. What we've done there, we haven't changed the value of the function, but we have introduced this 5 in the denominator, and so to cancel that out we need a 5 in front of this product, And now we can evaluate each of those limits individually. So the limit of that product of things is the product of the limits. The limit as x tends to 0 of the number 5 is just the number 5. The limit as x tends to 0 of 4x over sine 4x, we know that's going to give us 1. And the limit as x tends to 0 of sine 5x over 5x, we know that that's going to give us 1. So we're going to end up with 5 times 1 times 1, and so the limit of this function is simply 5. Right, we're almost done with different types. We need to look at absolute value type functions. These are always a little problematic for people. And the key to solving these is to break the function into two pieces. For example, if we are asked for the limit as x tends to -3 of the absolute value of x plus 3 multiplied by x plus 1 divided by x plus 3. Now remember that the absolute value of x plus 3 means that we evaluate what's inside these lines, and we eliminate any negative signs afterwards. So what does this function look like? Well, let's think about it. When x is -3, x plus 3 is going to be 0. We're going to get 0 divided by 0. So the function does not exist at -3. When x equals 0, we're going to have 3 plus 1 divided by 3, so x will equal 1. When x is equal to -1, the function is going to be 0. When x is equal to 2, we'll have 5 times 3, we'll have 15 divided by 5, so we'll have 3. And so our function's looking something like this. And when we are at x equals -4, x plus 3 will be -1, but the absolute value of that will be +1 multiplied by -4 plus 1 would be -3, and we're dividing that by -1, so we're going to get a value of +3 up here. And if you can continue plotting that, you'll see that it looks something like this. So this function looks linear to the left of -3, has a discontinuity at -3 where the function doesn't exist, and then looks linear again beyond -3. So we really need to break this function into two pieces on either side of -3. So the limit as x tends to -3 from the negative direction. So this means that x is a negative number, and so x plus 3 the absolute value of that would be equal to negative x plus 3. X is a negative number, magnitude larger than negative 3, so it's going to create a negative inside this bracket. But we're looking for the absolute value, so we're looking for a positive outcome, and therefore we have to put a negative sign outside for values of x which are more negative than negative 3. The x plus 1 stays the same, and the x plus 3 stays the same. And now we have our usual situation of a common factor, top and bottom. And as long as x is not equal to negative 3, we can cancel that out. And so what we're left with is the limit as x tends to negative 3 from the negative direction is equal to negative x plus 1. And if we feed in negative 3 into that expression, negative 3 plus 1 would be negative 2, and the negative value of that would be positive 2. And so we see that this function is approaching a value of positive 2 from the left-hand side, even though it never actually gets there. Similarly, to the right of negative 3, we can say that we're looking at the limit as x tends to negative 3, but from the positive direction. Now, if we're on the positive side of negative 3, then we know that the absolute value of x plus 3 is just going to be x plus 3. The absolute value sign doesn't actually do anything in this case. And so we can finish the function like this. And then, as before, we can cancel these terms, feed in a value of negative 3, feed in a value of negative 3, and we get an answer of the limit is negative 2. And that's what we show in the sketch of this function, is that when we're approaching from the right-hand side, the function is approaching a limit of negative 2. And so the limit of this function as x tends to negative 3 actually does not exist, because the value approaching from one side is not equal to the value approaching from the other side. So we've looked at a number of different approaches to solving limits. This should cover all the various scenarios that you will encounter, and hopefully this video has been helpful in understanding what is a limit and how to determine its value. Don't forget to like and subscribe if you've enjoyed this. Thank you very much.